Our planet's forests are remarkable places of resilience. For centuries, they have stood against storms, fires, and the changing seasons. Yet, in the last century, they faced a new, insidious threat. This threat came from the sky itself, in the form of acid rain. Pollution from power plants and factories traveled high into the atmosphere, mixing with water and falling back to Earth as a corrosive shower. This rain, laden with acids, fell upon the great forests of the northeastern United States and other parts of the world, silently stripping away the very foundation of life. The damage was not always visible at first, but it was profound and lasting. The acid rain acted like a thief in the night. It seeped into the ground, dissolving and washing away essential nutrients that trees need to grow strong and healthy. One of the most critical of these was calcium, a mineral that strengthens tree trunks and helps them resist disease and cold. As the years went by, the soil became impoverished, a shadow of its former fertile self. When these forests were also logged, the problem grew even worse. Cutting down trees removed the nutrients stored in their wood and leaves, and the disturbance to the ground hastened the loss of what little nourishment remained. The land was left scarred and hungry. To understand what happens next, we must turn to a special outdoor laboratory. In the White Mountains of New Hampshire, scientists at the Hubbard Brook Experimental Forest have been watching the land for over 60 years. They have meticulously measured the rain, the streams, and the soil in different parts of the forest. One area was left untouched, another was clear-cut decades ago and allowed to regrow, and a third was treated with minerals to help it heal. This long, patient observation has given us a remarkable window into the slow, complex, and often surprising process of a forest's recovery. It is a story of survival, but also one of hidden costs. The findings from this long-term study, published in 2025, have revealed a secret struggle happening right beneath our feet. For decades, we believed that once the acid rain stopped, thanks to laws like the Clean Air Act, the forests would simply bounce back to their former glory. The streams would run clean, and the magnificent sugar maples would thrive once more. But nature's recovery is rarely so simple. The forest did begin to heal, but it had to find a new, more desperate way to find the food it needed to survive. The legacy of acid rain had forced the forest to change its very strategy for life, with consequences that are only now becoming clear. Deep beneath the forest floor lies a world of quiet, relentless activity. Here, in the darkness, tree roots spread like a vast, intricate network. We often think of roots as anchors, holding the tree firm against the wind. But they are also miners, constantly searching for water and nutrients. In a healthy forest, the topsoil is rich with these essential elements. But in a forest recovering from decades of acid rain and logging, the soil is poor. The regrowing trees are starved, and in their desperation, they have turned to a more ancient and difficult source of nourishment, the solid bedrock buried deep in the earth. This is a process of survival, born from necessity. The trees are not alone in this effort. They are aided by a vast community of microscopic partners, fungi and bacteria, that live on and around their roots. Together, this powerful alliance releases subtle acids and enzymes. These substances work slowly but surely to break down the surface of the bedrock. They are targeting specific minerals locked within the stone, particularly a mineral called apatite, which is a vital source of phosphorus. As they dissolve the rock, they also release other nutrients, like calcium and silicate. This accelerated mining of the bedrock is a powerful display of life's ability to adapt and find a way to endure even in the most challenging conditions. This underground mining operation has a remarkable and visible effect above ground, particularly on the streams that flow through the forest. As the roots release calcium and other minerals from the bedrock, some of these nutrients are washed into the waterways. Since the 1980s, scientists have watched as streams in the regrowing forest have become significantly less acidic. The calcium acts as a natural antacid, buffering the water and making it healthier for fish and other aquatic life. In a surprising twist, the forest's own recovery efforts were cleaning the streams more effectively than even direct human intervention in a nearby watershed, where scientists had intentionally added calcium to the soil. However, this good news for the streams hides a worrying truth for the soil itself. While the bedrock provides a temporary fix, it is not a sustainable solution. The process of mining the rock and flushing nutrients into the streams means that these vital minerals are not staying in the soil where they are most needed. The soil's buffering capacity, its ability to neutralize acid and hold on to nutrients, is being steadily depleted. The forest is essentially sacrificing its long-term soil health for short-term survival and growth. This makes the entire ecosystem more fragile, creating a hidden vulnerability just beneath the green, regrowing canopy. As the chemistry of the soil changes, so too does the character of the forest. The grand sugar maples, famous for their brilliant autumn colors and the sweet sap that fuels New England's maple syrup industry, are struggling. These majestic trees require soil rich in calcium to thrive. In the impoverished earth left behind by acid rain, young sugar maples cannot grow as they once did. The new generation is weaker, smaller, and less able to compete. The very trees that have long defined these landscapes are now finding it difficult to hold their ground, a silent testament to the lingering damage done decades ago. In their place, another tree is rising to dominance, the American beech. Beech trees are tougher and more adaptable in these difficult conditions. They are exceptionally good at the underground mining we have seen, far better than the maples at pulling nutrients directly from the bedrock. Their shallow root systems and partnership with microbes allow them to scavenge what little nourishment remains in the depleted soil. As a result, in the parts of the forest that were cleared and left to regrow, the beeches have taken over. The forest is changing from a diverse mix of hardwoods into a landscape increasingly dominated by a single opportunistic species. This shift from maple to beech has significant consequences for both people and wildlife. For humans, the decline of the sugar maple poses a direct threat to a cherished cultural and economic tradition. The maple syrup industry depends on healthy, mature trees, and their struggle for survival casts a shadow over the future of this livelihood. For the animals of the forest, the change is just as profound. While beech nuts provide food for bears, deer, and other creatures, a forest dominated by one type of tree is less resilient. It lacks the variety of food and habitat that a more diverse ecosystem provides, making the entire food web less stable. Furthermore, this reliance on the American beech carries a grave risk. This species is currently under attack from two devastating diseases, beech bark disease, and the more recent, and even more deadly, beech leaf disease. Recent studies show that beech leaf disease is spreading rapidly and can kill up to 30% of the trees in an affected area. By replacing a diverse forest with a monoculture of beech, the ecosystem is betting its entire future on a single species that is itself incredibly vulnerable. A new wave of disease could devastate these recovering forests all over again, leaving them in an even weaker state than before. The story of these New Hampshire forests is a powerful lesson in unintended consequences. It shows that the impacts of environmental damage, like acid rain and deforestation, can echo for generations. Even after the pollution is reduced, the ecosystem carries the memory of the injury in its very soil. The forest's clever survival strategy, mining the bedrock for nutrients, is a short-term solution that may lead to long-term fragility. By depleting the soil's ability to buffer against future stress, the forest is left more vulnerable to a return of acid rain or the pressures of another harvest. It is a recovery built on a precarious foundation. This hidden vulnerability highlights the immense value of long-term scientific monitoring. The secrets of the forest's recovery were only revealed because scientists at Hubbard Brook had the patience and dedication to collect data week after week for over 60 years. Without this unbroken record, we would have seen the greening canopy and cleaner streams and simply assumed that all was well. This long view is essential for truly understanding how ecosystems work and for gauging the true success of our environmental policies. It reminds us that nature operates on a timescale far grander than our own, and healing is often a slow, complicated, and non-linear process. The discoveries at Hubbard Brook are a warning that extends far beyond the White Mountains. Regrowing forests all over the world may be facing similar hidden challenges. As we rely on these forests to absorb carbon and recover from past logging, we must be aware that they may be doing so at the expense of their own long-term health. This research compels us to think more deeply about how we manage our natural world. It is not enough to simply plant new trees or stop pollution. We must also work to restore the health of the soil itself, the very bedrock of a resilient ecosystem. Therefore, our responsibility does not end when a new law is passed, or when a clear-cut area begins to turn green again. We must remain vigilant stewards, continuing to watch, listen, and learn from the land. Protecting our forests means more than just saving trees. It means safeguarding the intricate, invisible processes that sustain them from the ground up. By supporting long-term research and adopting a more holistic approach to conservation, we can help ensure that these vital ecosystems do not just survive for the present, but have the strength and resilience to thrive for centuries to come, for the benefit of all life on Earth.